Okay, so first of all, I'd like to thank the organizers for inviting me to this conference and this nice place. So today my talk is going to be on supersymmetric index of black holes, and here is the list of my collaborators in this topic. So of them, Athira, Anupam, Chandramouli, Subramania and Sanurgabria are currently postdocs at various places. And Amitabh is a faculty member at the Chennai Biomedical. So let me give first a brief introduction to black holes and what is it that we want to study. So we'll start our discussion with a black hole in a general two-derivative theory of gravity in asymptotically flat d-dimensional space-time. And such a black hole can typically carry a set of U1 charges, which are denoted by UK, and the number of such U1 charges depend on the number of gauge fields, number of U1 gauge fields that the theory has. It can carry angular momentum, Gi, in the Cartan subalgebra of the rotation group SOD-1. And of course, it can carry a mass. And the mechanism of the entropy of such a black hole can be calculated by this formula, area divided by 4 times the Newton's constant. And it's typically expressed as a function of the charges, mass and angular momentum. And throughout this lecture, you should think of Q and J as having multiple components. Now, two derivative actions have a nice scaling property. Here that goes as follows. That if we scale the various tensor fields according to the rank like this, then the action scales by a factor of lambda to the d minus 2. Here the lambda to the d factor comes from the square root of determinant g, right? Because g mu is scaling with lambda square. And the minus 2 comes because you have two derivatives, and so you need an inverse part of the metric to contract with those two derivatives. So that supplies part lambda to the minus 2. And this scaling property of the action can be translated to a scaling property of the entropy in a d-dimensional space-time, and that goes as follows. Okay, that if we scale the charges and the mass and angular momentum in this fashion, then the entropy scales as lambda to d minus 2.
So, this scaling and rate of that time, so it's all about the number of indices, not about the actual mass dimension.
That's, yeah. Okay. So this scaling property just follows from number of indices.
So this would help you do a derivative expansion or something?
Yeah, it will, right?
Yeah.
But in two-derivative theory, you have this scaling property.
Okay, thanks.
So this suggests that if you want to take the macroscopic limit, which means the limit where the black hole is large, we can simply scale the M, Q and J according to these scalings and take lambda to be large. And in this limit, the black hole mechanism of entropy will scale as lambda to d minus 2. And the general program that we try to follow is to compare the entropy that we calculate from this formula with the log of degeneracy from some microscopic counting of the degeneracy of states.
Sorry, if you can for microscopic will be considered also we have ordered Newton's constant.
What are the Newton's constant? Well, if I am taking lambda to be large, then M can be larger than 1 over Newton's constant. Because the M has to be larger than the Planck constant. But it can be as, there's an upper limit on how large you want to take for macroscopic. Okay, so we'll also introduce chemical potentials, and these chemical potentials are defined in the way that I have shown here. So these are not independent parameters, okay? Because if we know the mass, charge and angular momentum, then the chemical potential is the inverse temperature, this is the chemical potential, and this is what this is the chemical potential conjugate to the angular momentum, which is also sometimes called angular velocity of the black hole. And just based on the scaling laws that I have given earlier, we can show that the theta, mu and omega scales in this fashion. And because Q and K can have multiple components, mu and omega also can have multiple components in general. Now these scaling laws are of course not sacrosanct. Because once you add hard derivative corrections, then the scaling laws will get modified, because now instead of using the Bekenstein formula, we have to use Wald's formula. So Wald's formula will give correction to the entropy from classical hard derivative terms, and that violates the scaling properties. Loop corrections also violate the scaling properties, because they can give additional terms of order log of lambda, which doesn't scale nicely when you scale lambda.
Ashok, one small question. On the previous slide, that temperature is not thermodynamic temperature, right?
This is thermodynamic.
It is. Then shouldn't that be internal energy with respect to the derivative with respect to m?
Yes.
Shouldn't that be the internal energy?
Well, it depends on what you keep fixed, right? Here you are starting with a microcanonical ensemble, which is where the entropy is given,
Yeah.
and then the inverse temperature is defined as the derivative of the entropy with respect to the energy.
Right. Yeah.
So that's exactly this one, right? Because you are taking the derivative of the entropy with respect to the energy. So this is black hole is a microcanonical entropy.
Okay. All right.
If you want to go from the grand canonical partition function, then you take the derivative with respect of the energy. Derivative of the energy, yeah.
Ashok, how do you motivate this, to consider this type of scaling properties?
Motivate meaning it just follows from the action, right? If you just look at the action, two derivative action, right? It has square root of determinant t, which scales as lambda to the t, and then it has the two derivatives have to contract with the inverse power of t. That gives lambda to the minus 2. Right? So total you get lambda to the t minus 2.
This could be made set in terms of symmetry of that.
I think it's not a symmetry because action changes.
Yeah.
But it's in some sense a trivial symmetry that it's just index contract. Right? The indices have to be contract to the inverse power of it, and that's all this is.
So can this scaling of beta, mu, omega also be understood in terms of index contract?
Well, this I got because we know already how these things scale, right?
Yeah.
And you just take the derivative, right? So from that you can get this. You can probably start with the index contraction and try to derive this, right? But I mean, it's easier to use these approaches to develop this scale. Okay. So as I was saying, by now there are many examples in string theory where this has been tested. But there is one open issue that remains, okay, which somehow was understood to some extent but not fully, and that issue is the following. So when we compare entropy with log of degeneracy, the computation of degeneracy is done by representing the black hole states as states of some brane system, right, which can involve ornamental strings, deep branes, and various other branes that actually exist in string theory. And we adjust the brane system so that it carries the same charge as a black hole. Right? If you have fixed the charges of the black hole, you make sure that the brane system carries the same charge. And then you simply count the number of states that this system carries. And you do this counting and with string coupling, in fact at almost zero string coupling, where you can think of the dynamics of the brane system just as a collection of harmonic oscillators. So the counting of states become more or less trivial. But the black hole description is valid only when the gravitational coupling is strong enough so that the horizon size exceeds the comparabilities. Right? So in the limit where the counting is done, okay, in that limit the black hole description actually is not valid. So then the question arises as to how can you compare the two expressions.
So in Shobhita, the way this is done is to using Cardi formula.
That's yeah. But Cardi formula you can also get from by representing this as a set of oscillators and power.
Yeah. But
Because
it is a
this
more.
Cardi formula we have field equal nowadays.
But the fact remains that it is valid for arbitrarily strongly coupled fields, the one only by the central charge.
But that description is only after weak string coupling. See, once you switch on the string coupling, right, and the CFT description itself is not valid, right? That gets valid.
But the follow that Robinson also didn't do an index, right?
They didn't do what hidden in the analysis is actually things. And you can justify it only because you can compare index.
Okay.
So the answer is that we try to compare supersymmetric index of BTS black holes, which do not change as you vary the number.
As the two dimensions, the growth is controlled by Carney's formula, and the central charge is protected as an anomaly.
Yeah, except that if you look at the limit in which the black hole description is valid, right? In that limit, Carney formula is not valid. Because Carney formula is valid only when H to be much larger than C, right?
Yes.
But the black hole description is valid when H is in fact much smaller than C. Right? If you look at the supergravity black hole description,
H is what?
H is a control way.
Why the mass is much larger than H squared? Why is it much smaller?
Because if you look at Q1, P5,
Yes.
P, right? And you take Q1, P5 and P of the same order
Yes.
for the black hole description you will valid. The central charge is Q1, P5
Yes.
and P is H,
Yes.
right? So the central charge is much larger than H because you are scaling Q1, P5 and P in the same order.
But isn't the dimension Q1, Q5, P? The dimension is 4.
Yeah, so the entropy becomes square root of Q1, P5, P.
I see.
But Q1, P5 is the central charge and the P is the control, right? So in that limit you cannot really use Carney formula. And I think the reason that the Carney formula is still what is because we are computing the index. Okay, so let me now say a few words about supersymmetric index. How does it help us? So for this, we consider a supersymmetric theory in asymptotically flat d space-time dimensions, and consider this quantity I. Here I'll extend these various quantities. So trace is a trace sum over all states. Okay, but this subscript means that. Okay, let me first explain what these various variables are. So J0 will denote some particular Cartan generator of SOD minus 1. Okay, it's chosen by us, okay, according to what we find most convenient. J prime will represent the Cartan generators other than J0. And now this trace is understood to be sum over all states, but at fixed values of Q, that means at fixed charge, at fixed values of J prime, okay, which means these Cartan generators other than J0, and 0 momentum, okay, which is K. And what comes inside this trace is this object e to the minus beta h, that's the standard Boltzmann factor, e to the 2 pi I J0 plays the role of a minus 1 to the n, right? Because J0 is the angular momentum, so you are denoting 2 pi in some 10. So this is essentially minus 1 to the n. It gives you 1 on bosons and minus 1 on commons.
So this K momentum is in the same in the B dimension momentum?
Yes.
But how can you diagonalize simultaneously the rotational Cartans and momentum?
Yeah, so you have to basically use those cases where which commute with J prime. Okay, so K refers to the momenta that commute with J prime.
Okay, but if I'm using all the J primes,
Yes,
all the Cartans of my rotational generator, then I cannot have any momentum.
that's it, yeah. But you will always leave out one. Right? In some cases, in fact, you don't. Right? In 5 dimensions, for example, there is no way.
Then because it's
Because if you take S2 to L times S2 to R, right, the vector is a spinner of or the sequence, right? So that is that never commutes. There is no component of K that commutes.
okay.
But in 3 plus 1 dimension, right, if you have rotation, you can still translate around the direction of rotation.
Yeah. So odd versus even.
Yeah, so odd versus even direction.
So by K you basically mean that extra direction.
Yeah, K is the momentum that commutes to J prime.
So I could take less J prime, more K also.
Yeah. Okay, and then there is this 2J0 to the n, right, which is perhaps a little surprising from the point of view of index, because if you didn't have this fact, then this is nothing but a weighted index, right? You are calculating trace of e to the minus beta h minus 1 to the n. So the purpose of this 2J0 to the n is the following. So one can show that if you take a trace like this, then this gets contribution from only supersymmetric states that break dual or less J prime invariant supersymmetries. So let me first and the second. So you take all the supersymmetries that the theory had, and then you see how many supersymmetries are invariant under J prime. Okay, you don't care about the ones that are not invariant under J prime. They play no role in this quantity. So look at the supersymmetries that commute with J prime. Then, if we have a state that breaks 2n or less of those supersymmetries, then those are the states that contribute to this. If it breaks more than 2n supersymmetries, 2n J prime invariant supersymmetries, then you can show that these states, or their contribution to the trace is just zero. So this means that a generic state, a generic non-supersymmetric state, which breaks all supersymmetries, will typically not contribute to this index, to this quantity I. But supersymmetric states of a certain kind will contribute because they may break less than 2n supersymmetries, 2n J prime invariant supersymmetries.
So if I take n to be higher than certain values, then
it's not useful because then
it is independent of n.
Exactly. Then everything will contribute. Right? It's independent of n after some kind of function. So you have to choose n judiciously. Right? If you take n to be too small, then the states that you want to count may not contribute. If you take n to be too large, then everything contributes. Right? Then this index is not correct. So you have to choose n appropriately so that you count, you don't get contribution from all the states, but you pick up the contribution from the states that you want to count, the supersymmetric states.
Sorry, I didn't understand. I mean, if I take n to be very large,
Yes.
then it gets contribution from states that break all or less supersymmetry.
Exactly.
So the state that breaks all the supersymmetries, those states will not contribute.
Those will contribute.
Because of minus 1 to the n.
No, those will contribute. Right? Minus 1 to the n will not take. 2j0 to the n, because of the 2j0 to the n, states will break all supersymmetries will also contribute. Because minus 1 to the n, what it does is it bears bosons and formulas, but this 2j0 to the n takes different values for bosons and formulas, right? So if you take n to be too large, then every state contributes.
So it's not index anymore.
It's not an index anymore, so it's not very useful.
So you just have to take one less than that.
Yeah, you have to take appropriate number so that it counts the states that you want to count, right? Which in typically are the states that deserve force supersymmetries. Right? Break the rest. So you choose any appropriate. So for example, if you are trying to want to say n equal to 4 supersymmetric theory in 4 dimensions, right? That has 16 supersymmetries. The black holes which you typically want to count, these are 4 supersymmetries. So you break 12 supersymmetries, right? So you pick n equal to 6.
Can n be half integer here?
Pardon?
Can n be half integer or is it integer?
In half integer, I mean there are no known examples where the number of broken supersymmetries is odd. Right? Typically the kind of states that one wants to count, you always have even number of broken supersymmetries. But you can, I mean of course define this with odd integer.
So Ashok, what you have in mind here is the supergravity theory in fact in asymptotically flat dimension, and then this trace is on some flat space or in the
Yeah, we are always counting from asymptotically flat from infinity, right? So the states are always counted from infinity. So it doesn't have to be supergravity, it can be superstring theory. So any UV complete theory whose spectrum is well defined.
supersymmetric field theory also.
Supersymmetric field theory, yes. So this can be used for supersymmetric field theory.
Yeah, right. No, but I guess you would be interested in matching this with the black hole theory.
Exactly, yeah.
So in that case, is it that what is being matched to what?
So, for example, the counting, the microscopic side, you can calculate this. Okay? Because you know the state that just harmonic oscillators, you calculate what K0 value they can carry and calculate this case. And that you have to now compare with the index on the black hole side. And I'll describe how to calculate the index on the black hole side.
So I didn't quite understand. Microscopic counting then would be what? Let's say I have some field theory. Let's just consider a field theory in 4 dimension.
Yeah.
Equal to supersymmetric field theory, let's say. Now I can define this quantity in flat space, I can compute it, and then this is to be matched with what?
To the black hole.
But it's a field theory, there is no.
Oh, field theory is just definition. It doesn't have to be matched to anything. Right?
Okay.
That's the index
Okay.
of the quantity.
But if you want to match it, you want to consider gravitational.
Exactly. Because gravitational theory has these two different descriptions, right? Because there is a black hole description and then there is a microscopic description. that's where it becomes non-trivial, right?
So in the microscopic description, you just have these wave harmonic oscillator corresponding to each mode, and then you just want to.
Yeah, you just count, you just classify the supersymmetric states,
Okay.
see what J0 value they can, right? Calculate these states, and that's it.
So that's just the Fock space of oscillators.
Exactly. Fox will. Okay, so n equal to 0 is a special case which gives a Witten index. But from this you can see that those count only those supersymmetric states which don't break any supersymmetric. And those are basically the vacuum states. So Witten index counts the number of atoms. Okay, so I'll define this quantity S BPS, right, which is the entropy unit codes of BPS states by this form. Right. So here, because we are tracing over zero momentum states, this minus e to the minus beta h you can just replace by minus beta times N BPS, okay, which is the mass of the supersymmetric states. And then the trace over the down state is what I am calling the S BPS. This basically is the counting of the number of black hole states with signs. Number of, well, not yet black hole, number of states, supersymmetric states with signs.
I'm sorry, why do you say all the states in the trace will have the same mass?
Because supersymmetry fixes the mass in terms of the charge.
But then you're looking at states which take different levels of supersymmetry, right? You have the.
Yeah, but typically what happens is that if you fix the charge, at that charge, you find that the states break only one kind of supersymmetry.
Okay.
For example, if you are looking at certain kind of black hole states in n equal to 4 supersymmetric string theory or n equal to 4 supersymmetric field theory, right? If you put both electric and magnetic charges, okay, generic electric and magnetic charges, you find that supersymmetric states are always quadratic states. So you have those kinds of states.
I see. Okay. So phenomena is just 2n, not 2n.
Exactly. So half BPS states could contribute, right? But there are no half BPS states which carry both electric and magnetic. Okay, so here there are just some examples that in D equal to 4, the rotation group is SU2. So J0 we can take to be the third generator of the rotation group, and J prime in this case is trivial. In D equal to 5, the rotation group is SU2L times SU2R. So you can take, for example, J0 to be J3R, and then J prime will be J3L. Okay. Now, on the microscopic side, we can easily compute the index because we have harmonic oscillators, right? So we have explicit description of all the states. You can just count what J0 eigenvalue they carry and calculate this index. The complication is that if you want to compare this index between the microscopic side and the macroscopic side, then on the black hole side also, we need to calculate the index. But what we can calculate typically is not the index but the degeneracy, because the Becken-Stocking entropy is supposed to give the log of the degeneracy. So then the question is, how can you compare index, the microscopic index, with macroscopic degeneracy? The reason that you want to compare the index is because index is what is protected between the strong and the weak coupling. And here there is a hidden assumption that one uses, and that is that index and degeneracy are equal at generic coupling. Okay, not at zero coupling. At zero coupling, there are certain examples where index and degeneracy are not the same. But one expects that at a generic coupling, okay, perhaps anything that could become non-supersymmetric will become non-supersymmetric, and only the index of outcome states will remain in the lowest energy state, and that's what we count. So the black hole indeed counts degeneracy, but degeneracy is equal to the index at generic value.
So this J0 to the power n insertion, doesn't that spoil the fashion? Because one state could contribute not just one number.
Yeah, but the way it is set up, right, when one actually does a calculation, one finds that J0 to the n basically gives a simplified multiplier. Because the point is you have to use the J0 to the n appropriately, so that the cancellation between the Forduans and bosons don't take place. Right? Because otherwise, the Forduans and bosons will just cancel. Because we are considering a supermultiplier, right? These states are supermultipliers, so the supermultiplier has both Forduanic states and bosonic states. And you have to be careful not to cancel them. So So J0 basically goes in ensuring that they don't pass. So even though it looks like J0 to the n is a non-trivial factor, it actually comes out as a trivial factor.
So this also assumes that it's an exact degeneracy, that's not some kind of macrocanonical window for which you've calculated.
Yeah. So this assumes an exact degeneracy for supersymmetric states indeed. Right? Otherwise you can say index will be 0. Right? If there is no exact degeneracy, the SBPS will be 0, right? If there is any terms. And you can check by microscopic calculation that there is the index is non-zero, right? Which means that there is an exact index. Right? Because non-zero index means that they cannot just get it. Okay, so the question that we want to ask is it possible to do better by computing the index on the planets? And this is what I am going to describe now. Okay, this was developed in the last few years by starting with the work of these authors. So I will describe how one can go about computing the index on the black hole side. And this will be done via the usual Gibbon-Stocking gravitational path integral with a slight twist. So here is the idea. Okay, the idea is very similar to what Gibbon-Stocking introduced when they tried to compute the entropy from gravitational path integral. So here we will be performing a path integral over all fields weighted by exponential of minus action. The extra ingredient is that we will put a 2j0 to the n in the path integral. And for when you carry out a path integral, this is the Euclidean path integral, we have to put the asymptotic boundary condition on the various fields. And the boundary condition will be the following. So first of all, we will compact it, we will make Euclidean time periodic with period beta. But this period will also have a twist. So the azimuthal angles phi will also be identified. So the identification is not tau is equivalent to tau plus beta, but tau phi pair will be identified as tau plus beta and phi minus I omega beta. Omega, if you recall, has multiple components and so does the azimuthal angle. Okay. So this equation makes sense. You will just shift the azimuthal angle by this. The I is square root of minus 1. Okay. So these two are a little surprising. But in Euclidean path integral, of course, one has to, the standard points are all complex solutions. Okay. So that's the way you have to interpret this. That we periodically identify the phi coordinate with period I omega.
Should we add 2pi because of the integral 2pi I zero?
Pardon?
Should there be an extra 2pi because of the...
Yeah, I'm coming to that.
Okay, sorry.
That is a part of it. And similarly, we have to put the information about the chemical potential mu, right? So this omega is angular velocity, right? That is the chemical potential dual to the angular momentum, and the chemical potential dual to the gauge field, dual to the charges. That comes to the following boundary condition. So the time component of the gauge fields take asymptotic values given by A tau equal to minus I. And finally, omega has, as I said, can have multiple components, but omega 0, which is the component that is conjugate to J0, is chosen in this very special way. We choose omega 0 to be minus 2 pi I over beta. And what this does is that it computes this partition function. Right? This is exactly the Gibbon-Stocking result, except for this 2j0 to the n factor that comes because in the path integral we have inserted this 2j0 to the n. And this condition, beta omega 0 equal to minus 2 pi I, basically means that part of this, minus beta omega dot j, has become 2 pi I j0. So this is the beta omega dot j, the part of beta omega dot j for all omega and j other than j0. Right? That's the Cartan algebra outside j0. And then because of this condition, you have this factor of 2 pi j0.
So this is a complex geometry.
They compute a complex geometry. Right? So you the asymptotic boundary condition is already introducing a complex boundary. It will be a complex. The rotating black holes are typically complex. Right? And once you have introduced angular momentum, right, the Euclidean solution becomes complex. Okay. So what we are going to do is to analyze this formula both from the statistical side and the gravitational side. And I will explain what.
So you're saying that rotational rotating black holes in Lorentzian space when you analytically get in the nuclear space, this is what.
Yeah. That's the way Gibbons Hawking arrived at this problem. So first let's look at the statistical side. Right? According to Gibbons Hawking, this is what we are computing. Okay, the trace over all states. But now recall that we have already defined this quantity to be S BPS by the partial trace. But take the trace but keep Q, J prime and the momentum fixed. So we can now express Z in terms of this S BPS by simply performing the trace over Q, J prime and K separately. Okay. So Z will be given by the trace over Q, J prime and K weighted by E to the S BPS minus beta times N BPS. Now the difference is here you have H, here you have N BPS, so we just put the kinetic term for the black hole, right, which is the kinetic energy, and it turns out that because you are looking at the macroscopic limit, it's enough to keep up the quadratic term. And then this minus beta omega prime dot J prime and minus beta omega dot Q comes because these are just there here, which are not there in this case.
Sorry, but what if the number of states depends on Q and J prime?
What?
Why, the number of states might depend on Q and J prime, right? So would you generally say have...
Yes, so S E to the S BPS is a function of Q and J prime.
Oh, the switch Q J prime, okay, sorry.
Yeah, so this is a function of Q and J prime.
Okay.
So that's what goes in here, right? I'm not just reading this.
Yeah, sorry.
And Q and J prime are typically discrete quantities, but in the approximation that will be working, we can just think of this as formula. Okay, but if you want to be completely accurate, you should really write it as sum over Q and J prime instead of anything else.
So I didn't quite understand the logic. So when you say the second line, this assumption is being used that the index is the same as DLSC?
No, because it's not the definition, right? If you look at how I define E to the S BPS,
So that's the definition, is it?
yeah. So E to the S BPS, that is the index, basically, right? This is counting down states up to with weights, right?
Okay.
That's the definition. Right? That definition is what I'm doing in the given sum part.
So we don't know what that is, right?
We don't know what that is. We can do the count. We can calculate it from microscopic side,
Yeah.
right? Otherwise, we don't know what that is. Yeah, from the macro side, we don't know what that is. Our goal is to figure out what that is. Okay? That's what we have to do. Right now, you can think of SBPS as the unknown object as far as the gravitational side is concerned. But you have to try to figure out how that.
But then Z is expressed as a function of, as an integral of this unknown.
Yeah, and the function integral of that. Okay, so NT basically is the number of components of T, right, which commutes with this omega prime dot J prime. Okay, because otherwise otherwise of course you can simultaneously diagonalize the momentum. NC prime is the number of quantum generators, J prime, and that's the integral here. And NV is the number of U1 gauge fields, right, that's the same. So here is again the statistical expression. You don't, as I say, as Vijay said, you don't know what this is. If you had an answer from a microscopic side, then of course you know what this is. But just working on the black hole side, you don't know what it is. Right? You will see how to calculate this. So the contribution to this integral is dominated by the saddle point where the integral has an answer. So which means that you have to basically extremize the exponent with respect to Q, J prime and K. For K it's easy, basically it's K equal to 0 is the saddle point, right? Because you can see that there is quadratic, false of quadratic into the minus beta K square. So the K integral will produce a factor of MBPS over beta to the NT by 2, right? That's Gaussian integral, which is given here, right? So here I have put in things in terms of lambda, because I know how MBPS scales and how beta scales for large black holes, and that's where this number comes from. Similarly, Q and J integrals, it can also be done by the saddle point method. Right? You just expand around the extremum and you pick up the determinants of these matrices. And again, because you already know the scaling of SBPS, which is Q and J, we can find out the lambda dependence of these, and that's very good.
So Ashok, at the beginning, didn't you explain that the lambda dependence was only approximate?
Yes, indeed.
So,
So at a quadratic level, the exponent scales in a certain way.
yes.
Right? So if you are doing a large lambda expansion, right, this is a correction to the lambda scale.
I see. But how do you know these corrections will not be important in doing microscopic matching?
Well, we do the microscopic matching for large lambda, right? The way the microscopic matching is done typically, then you, from the black hole side, you do a lambda expansion.
So you can think of this as you're in a regime where the high derivative corrections and loop corrections are not important.
And so on. Not that they are not important because you want to keep track of them and match, right?
Yes.
But they are treated properly. The higher dependent loop corrections. I mean, if we have time, we will go get to an example where this can be done, right? Where you have to really think of higher derivative terms, non-quadratic. Right? But at this stage, I am thinking of treating the higher derivative terms quadratic. So it makes sense to say what is the leading contribution, that is the Beckens-Hopkins that comes on the leading Beckens-Hopkins answer, and then there are some leading.
But then when you keep track of the subleading corrections, you have to go back to this integral and make sure that there are corrections to the scheme.
Indeed, yeah. So the log lambda, right, the leading log lambda will come just from here.
And the leading will come from there.
Right? Then that will lambda log lambda,
Yes, yes.
right, from the higher, indeed. So you have to keep track of the whole expansion.
So what is NV and C?
Oh, these are the number of integrals. So NV was the number of U1 gauge states.
Okay.
NC prime was the number of Kaplan generators which are outside K0. So basically one less than the total number of Kaplan generators. And this is the number of momenta that comes to this omega prime. Okay, so now if you look at the saddle, compare the saddle point value, you can get log Z. So this is the leading answer, right? Just pick up the exponent at the saddle point. And then there is this correction which is proportional to log lambda, because this you can exponentiate and you get some coefficient times log lambda, right? And that coefficient is 0. So this subscript E basically is to emphasize that this log lambda correction is coming from the change of ensemble, right? Because this is essentially changing from microcanonical to grand canonical ensemble, which is why okay, which is the reason why you get to get this log. Okay, so now let's analyze the same thing from the gravitational side. Right? So Z is given here. Now here, so you are doing a path integral now. Right? That path integral over all the fields. And in that path integral, you have put boundary conditions, right? Which we understand from given something. But there is also this factor of 2J0 to the n. Right? Now the question is, what does this 2J0 to the n do from the gravitational path integral? And what it does, in fact, is quite simple. Because we expect that the gravitational path integral will get contribution from configurations which break supersymmetry partially. For each broken supersymmetry, there will be a Ford 0. Those Ford 0 integrals will just make the path integral vanish. So if you didn't insert this 2J0 to the n factor, right, you will not pick up any contribution from that. Okay, because those will just vanish by Ford 1 path, the path integral of Ford 1 0. So this 2J0 to the n essentially saturates those Ford 1 0 integrals. Right? And that's the purpose of this 2J0 to the n factor as far as the gravitational path integral. But once you understand that, you can basically forget about this 2J0 to the n. Right? That they just want to absorb the Ford 1 0 mode integral. And then we can use again the given something inside, okay, to find log Z as the contribution from the Euclidean black hole sample this time. So this is the given something result. So up to this point is a given something result. Okay. This is a rotating black hole entropy. It's rotating because you have inserted all these chemical potentials or dual to angular momentum. This is also rotating black hole mass. These are the usual terms which are appearing in the exponent. And then this C log lambda is a contribution from one loop quantum correction. Right? In the given something path integral, if you carry out the one loop quantum correction, then the massless fields running in the loop give a term proportional to C log lambda.
Ashok, one question.
Yes.
What is the mechanism behind supersymmetry breaking here?
So the black hole breaks some supersymmetries.
Because of.
Because black hole only preserves that when you construct a Euclidean black hole solution, right, which is saturating the path integral, it is not invariant on all the supersymmetries. So it's not supersymmetry breaking in the vacuum. Right? It's just a given configuration breaks certain supersymmetries. Then you basically solve the Killing-Spinner equation. In that you find the Killing-Spinner solutions is not maximal. Right? Suppose you start with 16 supersymmetries. The black holes, typically what will happen is that you will break 12 of the 16 supersymmetries, you will find only 4 Killing-Spinners.
So this is explicit breaking.
Not explicit breaking, it's still spontaneous breaking.
Spontaneous, yeah.
But spontaneous, you are also breaking transition invariance, right?
Okay.
Because black hole is a localized solution. Right? So just like you have transition in zero mode, you also have supersymmetry zero modes.
Okay. So these are Goldsteinos.
These are Goldsteinos, right? But these are localized Goldsteinos. Right? These are Goldsteinos localized on the black hole solution. Right? Asymptotically, when you go far away, then of course you see supersymmetry in the vacuum. Right? It's a localized solution is breaking supersymmetry, and these are the Goldsteinos for that. Okay, so now we are going to combine these two results. So this is the gravity result, this is the statistical result. And now we see that we can compare this and get a formula for SBPS, which is given. This part you can ignore to leading order, right? Because this is the logarithmic correction. You are only interested in the order lambda squared term, which is the leading contribution. You can just focus on this part. And in fact, you can further equate these two, M BPS and M rotating black hole, because this is getting contribution from supersymmetric black holes, and once you have supersymmetry, then the mass is fixed in terms of the charges. The BPS mass is also the mass of the black hole that will contribute to this atom. Okay, so you have M BPS equal to M the rotating black hole solution, but this is a non-trivial part of the result, that this now tells us how to calculate this index or the log of the index from the black hole side. Right? Because this you can calculate from the black hole side, this is just rotating black hole entropy with certain properties. This you can calculate 2 pi I J0, because once you say beta omega 0 equal to minus 2 pi I, J0 will get fixed. And then there are these logarithmic constants. Right? Part of it is coming from the gravitational path integral, part of it is coming, which is coming from the change of answer.
So how would the J0 get fixed, you said?
Because we set beta omega 0 equal to minus 2 pi, right? So you are fixing omega 0.
Okay. Yes.
So omega 0 and J0 are not independent, right? Because you can either take omega as independent or J as independent. Right? So once you have fixed omega 0, J0 gets fixed.
Can you make like at least like non-supersymmetric gravity? Like there are these boundary conditions which is microcanonical ensemble, canonical ensemble.
Yes.
Can you make a like even in this case? Can you make a like easier by going to calculating the gravitational?
Yeah, I have thought about it a lot, but I don't know how to do it. Right? If you are only interested in the leading answer, you can do it by having some boundary.
Right.
But when you want to go beyond the leading order, right? When you are looking for all these log lambda corrections, then you have to fix the boundary condition on the fields asymptotically, right?
Yeah.
And when you go from microcanonical to canonical, you have to change the boundary condition on the fields. And it's not clear how to systematically do the path integral of the fields if you use unnatural boundary condition, right?
Okay.
Normally you just put normalizable boundary condition, and you keep the normalizable modes, and you know how to do the integration over the normalizable modes.
I see.
So that's why when you are looking at the full asymptotic black holes in asymptotical flat space time, the natural ensemble is the grand ensemble. Right? But I have to fix it.
No, but
There's
one
a
can
further
do that.
subtlety with this, I think.
Pardon?
There's a further subtlety with this, which is I think the canonical ensemble itself. In this case, we have a supersymmetric case where degeneracies are exact. But in general, the canonical ensemble itself, the microcanonical ensemble is not very well defined. Because you have to specify also the width of energy.
I agree.
And so maybe there is no natural path integral definition.
True. Yeah. So I mean, right now let's stick to supersymmetric technique. Otherwise, it's only approximate, right? Because after all, black hole is also unstable, right? Difficult. So it's not clear what exactly you are calculating. Right?
Even in the first place, when we talk about the index in the CT side or just the microscopic side, There we could have just defined it with the canonical, I mean, grand canonical ensemble, right?
We could, yeah.
And then it would not need this translation.
That's it, yeah.
So
So
why
you
is
could
that-
calculate this in the grand canonical side, right?
Yeah.
That basically the end of the C,
Yeah.
right?
Yeah.
The C will come somewhere else, right? Because you will be calculating log Z directly. So that C will go away, but log Z will have that information also. But naturally, you want to do the counting, right? It's easier to do the microcanonical counting because you are really counting states. Okay. So then, this is the result. Okay, and now the point is that this can be tested in various ways. The right hand side, there is a confusion, right? This has to be calculated using rotating supersymmetric black holes, beta omega 0 equal to minus 2 pi I. And so if the microscopic result for the index is known, then the left hand side can be computed as log of the index directly. Right? SBPS, you can do the counting, 0 minutes. So I think this covers the formal part of this, right? The examples I'll just go through. Okay. So the right hand side has to be computed using rotating supersymmetric black holes with this beta omega 0 equal to minus 2 pi I. So as I said, the microscopic result is known, then the left hand side can be directly computed compared to log of the index. But if the microscopic result is not known, what you can do is you can still compare the right hand side with the entropy of an extremal zero temperature black hole with VR horizon against to geometry. Because this is what computes the degeneracy of these black holes. Right? If you are only interested in calculating degeneracy, then you don't need to introduce all this pi I, J0, etc. You directly compute the entropy. You don't need to use this rotation J0. So you can calculate the left hand side that. So if you didn't know what SBPS was for microscopic computation, we could still ask that does the left hand side agree with the black hole entropy, which is extremal zero temperature non-rotation. Okay, so these are the two ways of doing this comparison.
So could you say this again? So I understand that if you had a microscopic computation, then you could just check this.
Yeah.
The right hand side is gravity, left hand side is microscopic counting, and then you can see whether.
Yeah.
And then if you don't have that, then what else can
Yeah.
you do?
Then you are asking, does the entropy agree, does the index agree with the index? Now the both calculations are done on the black hole side. I told you how to calculate the index, but you also know how to calculate the degenerates, right? That's from Vegas now. Right? Where you don't introduce this equal to pi I J 0. Right? So beta omega not equal to 0, right? You don't have to introduce this chemical coefficient. So you take a non-rotating black hole there, right? Which has the usual extremal non-rotating black hole with VR horizon against geometry, and you can get calculate it.
But if that were true, that means that SBPS just is equal to S.
Yeah, so if that's not true, then that means that we have tested the degeneracy for the index hypothesis by doing the calculation both sides from black holes.
So that means the last two terms should go to 0.
Last two terms, these two, no, this will not go to 0. That's a non-trivial statement because okay, this part of course is extra. Right? Let's forget about this part now. It says that if we calculate a non-rotating supersymmetric black hole of certain charge, and if you calculate the rotating supersymmetric black hole in certain charge, in the same charge, but with beta omega 0 adjusted to minus 2 pi I, and add the rotating black hole entropy with 2 pi I J 0, then the result should match. Okay, so I think since my time is up, I'll just give the list of cases where it has been tested. So the simplest one is classical two derivative theories, right? Where you can test the second hypothesis, that whether the index is equal to entropy, right? So this relation in particular. So you calculate the left hand side using the non-rotating black holes, the right hand side using rotating black holes, and see if this relation holds. And this has been tested, for example, in minimal n equal to supergravity, n equal to supergravity, and d equal to 5, general n equal to supergravity, d equal to 4. Second, it has also been tested in classical theory of higher derivative terms. That you take n equal to supergravity with certain class of higher derivative terms added to it. Again, you can calculate the right hand side using rotating black hole in any supergravity with high derivative terms. Now all the entropy calculations have to be done using Watt's formula because we have high derivative terms, right? So lambda scaling is not there. There is a correction to lambda. And the left hand side you can calculate using the non-rotating black hole, right? Which in fact had been done long time ago by these authors, right? Using the attractor mechanism. And again you find that the two sides again, right? One side you use non-rotating black hole, the other side you use rotating black hole, and indeed index and degenerates formulas. Third, the logarithmic corrections have been tested. So this calculation, this I have already told you. So C, of course, there is an explicit formula that I have written down. The C you can calculate from the one loop determinant of massless particles in the rotating black hole background. On the other hand, on the left hand side, right, if you have a non-rotating black hole, there again you can calculate the one loop determinant of massless fields. But this time you can just focus on the near horizon areas to consider geometry, and you can calculate the logarithmic corrections here. And even though the intermediate steps are quite different, you find that indeed the two sides exactly match. And the surprising part of this is that on the left hand side, the calculation is done directly in the microcanonical ensemble, right? Because for extremal black holes, you are already in the microcanonical ensemble. So there is no log from change of ensemble. All the logs on the left hand side come from gravitational path. Whereas on the right hand side, part of the logs come from gravitational path integral, that is C, and part of the logs come from the change of ensemble. So somehow the gravitational path integral already knows the effect of change of ensemble. Right? So the gravity in some sense is knowledgeable about statistical mechanics. And final set of states where it has been tested are small black holes. Right? These are so this is a case where you cannot do derivative expansion anymore. Right? You have to actually treat all the higher derivative terms together. And again here one can correctly reproduce the microscopic results up to the overall numerator. So this I think I will not go through that.
You can't use the approximation you used for doing the J equal to its.
Here? Yeah. So here we didn't even go to logarithmic correction, right? We just do saddle point. And at the level of the saddle point, what happens is that the solution that we find, right, is the horizon is big in most places, right, where the scaling works, but it has some singular points. And near those singular points, you cannot use the scaling anymore. Right? There you have to treat all the higher derivative terms in the same way. Nevertheless, there is a modified scaling law that you can find here, right, which determines the dependence on all the parameters of the black hole, the mass, charge, angular momentum, everything, as an overall factor, right, which is completely determined. And what remains undetermined is just one numerator factor in this case. Yeah, that matches with the microscopic result for counting of states.
So if you complexify chemically your 10D torus, what is left?
10 minus d dimensional torus. Not 10d. 10 minus d dimensional torus. So here the point is in this 10 minus d dimension there is a counting formula that is known. Right? And that leading down the counting formula is independent of the dimension d. Right? And that comes out from the black hole side of the analysis, even though the black hole itself looks a d dependent of. Right? So when you define d, the black hole solution is very different. But once you go to the scaling limit, you find that the d dependence factors out. Yeah, then you get completely inverse response. Okay, so I think I'll just
More questions? One quick question. So I didn't quite understand this matching with the non-rotating black holes.
okay.
So the rotating black holes would give you give us the index of the counting of the states with some Mandelstam.
Yes.
Right? And then why is it that we are matching it with the non-rotating black holes?
Yeah, because it gives the degenerates. Let's suppose that we
But of different states, right? So the states
No.
don't have.
the same charge. Okay, let's simplify. Minimal electron loose pattern, right? Where you fix the electric charge and you say what is the how supersymmetric state the fixed electric. Right? You will calculate the Reisner Nordstrom black hole, right? Go to the extremal limit and calculate sets. Right? There's no rotation there. Right? That's the Ashoke Sen formula. So that will be given as a function of a charge.
Yeah.
That is that. Now you ask how that you want to calculate the index.
But of the spinning states, right? Of the states that carry J.
K0 is straight forward. Right? In 4 dimensions there is no K. There is no J prime, right? There is a one angular momentum that you are tracing over, right? So that information is not there. You just calculate trace of between 2 pi I J0, right? There are 2 J0s to the end. But because you have between 2 pi I J0, you are setting beta omega 0 equal to minus 2 pi I. The saddle point that contributes in the rotating side.
I see.
You take the rotating side.
Oh, I see. I see.
It has a defined entropy. So that doesn't agree with the non-rotating Blackmore entropy. But you calculate also J0. And then calculate the rotating Blackmore entropy plus 2 pi I J0. And that you find agrees with the non-rotating Blackmore. So that's the simplest case of this form. And the others are just more complicated parts of this.
So I guess you gave a list of examples where this degeneracy equals index works. Are there
Yes.
examples where it doesn't? Or
I don't know of any example where it doesn't.
okay.
At least to the, see, this is being done at the leading order. Right? Maybe there are sub-leading orders where it fails. Right? But leading and the first logarithmic correction, I don't know of an example where it doesn't work. And that also explains why in all the earlier cases, right, where the degeneracy was computed with the log of the index
From the
macroscopic side, right? Why that one? Right? Because somehow the degeneration index on the black hole side seem to always come out to be the same.
But your proofs are all by example. You don't at this point have a general proof.
No, there is no general proof, right? I mean, it should be possible to find a general proof at least when the classical two derivative action, right? We are asking to take a classical two derivative action. We have two quantities. One is a non-rotating black hole, right? Extremal non-rotating black hole with the entropy you know how to calculate. The other one is a rotating black hole, right? Not extremal, but it has its rotational parameter is fixed because beta omega 0 equal to minus 2 pi, right? We calculate the entropy of that plus add 2 pi I J0. That is supposed to be equal to the entropy of the non-rotating black hole. Right? This is a purely classical statement, right? And it should be possible to prove it from just classical analysis. But so far there is no general. This has been only tested in examples.
There is a symmetry-based argument that you are doing when the index should be.
Yeah, but that is a microscopic argument, right? That at a generic point in the moduli space, right, or generic coupling, you would expect that all the states that could become massive will become massive, right? Leaving only the minimal number of previous states in the previous state. And then, of course, index and degeneration.
And is the statement about fixed topology referred to? Like suppose you're in 5D and you have different topology?
Yeah, so typically if you have black rings, etc., those are exponential subdominant. So it will be good to check what happens for those cases. Right? It's not even clear whether the black rings, for example, contribute to the index. Right? This has not been checked.
So you mentioned that in the Sturm-Jaffa case, this H is actually much smaller than C.
Yes.
Remember, there was a paper where by Hartman, Stoic,
Yeah.
where they showed that at least if H scales with C, there's this extended range of validity of Cardy's formula. But you're saying that there's in the case of Sturm-Jaffa, it's even extended beyond this.
Yeah. The H, in fact, is much smaller than C. Right? Because you have these three charges, right? And the supergravity regime is where all three charges are of the same order.
Yeah.
Right? They are all becoming large. And in that case, H goes as linear in charge, whereas the C goes as quadratic in charge.
So I guess so in the context of alias free black hole, in the context of BTZ black holes, we sort of know that the Cardy formula directly matches with the BTZ black hole entropy, and there's actually no input there on how big the black hole was.
That is
so
it
could even be below the Hawking page transition. Sort of the formula seems to work, even though it's not just.
That's
Is that possibly related?
Yeah. So here, I mean, I think Kolchinski had some argument based on a 6-dimensional. So he I mean, trying to explain why the Schrodinger calculation worked. But here, instead of thinking of 5-dimensional geometry, you have to think of it as a 6-dimensional linear horizon geometry, where there is an ADS-T. And based on that ADS-T, and you can argue for cardinal.
There's something I didn't understand about an answer you gave during the talk. So if you think, let's think of global ADS-3 cross S3 cross T4.
Yes.
And I thought the black hole first appears at Q1, Q5, Q4. That's the lowest black hole threshold.
Okay.
And then if you take the temperature to be very large, then the black hole is much heavier than Q1, Q5. So why do you say that it's much lighter than Q1, Q5?
If you take H to be much larger than Q1.
Yeah, you can take H to be much larger than Q1.
Yeah, but I'm saying for a 5-dimensional supergravity do point. Right? That's not a non-singular. Right? From the near horizon ADS-T term is still geometry.
Yes.
Right? You can try to explain why it's not.
Yes.
And that's what Kolzinski tried to explain.
Okay. So from the near horizon point of view, you're saying there is not. If you think of a black hole asymptotically ADS-3, then there is no mystery.
That's yeah.
Oh.
But if you think of this as asymptotical 5-dimensional black hole, then there will be an issue because from 5-dimensional perspective, the black hole description is valid only for all the charges.
Okay, let's thank Ashoke again for